Hey AP Chemsters, this is Mrs. Vanderwall bringing you the third installment of the blank wall series for section 13.4. So let's continue on with problem number 16. Here we have this butadiene. It's going to become CaH12. Here is the reaction. So basically it says, according to the following graphs, is this reaction a zero, first, or second order? So looking over here, don't look at your data, look at your graphs. A zero order, that's where you'd have a graph of just concentration versus time. We don't even have that, so it's not zero order. A first order is where you have the natural log, like this one over here on the left. And looking at the graph, though, is this a linear graph? No, it's not. It'd be first order if it were a linear graph. That's why we could talk about y equals mx plus b when we discuss that. So it's not linear. It is not first order. So about second order, we have the 1 over concentration. Is it a linear graph? Yes, it is. So this is going to be a second order reaction. So let's scroll down here. And it says, what is the value of the rate constant for the reaction? Well, if it is indeed a second order reaction, we need to use the second order equation. And like we just said before, that if it was second order, we're talking about 1 over the concentration. This is why it's linear, because here is your y, mx plus b. Notice that again, k is a positive value, and if we're to go back up here and look at our slope, it's a positive slope. So again, this all relates. So now what? We got to plug in some values. You have a choice. Looking at the data up there, the very first one is your initial rate. Leave that one alone. We're going to put that in for the b value. Pick any other of the data, and we should all get a very, very close value for k. So go ahead, pause this, and pick one of those data points, and you figure out what k is and see how we do. Okay, so hopefully you've continued and finished off problem B, and let's see what's going on here. So I picked the very second problem, or the second data point, where the concentration is 0.00625 and the time was 1,000 seconds. So now I'm just going to do my math and plug this in. Now notice, when I did the math, the 1 over 0.00625 is 160, but the molarity stays in the denominator. Same thing over here. When I went 1 over 0.01, that equals 100, but the molarity stays in the denominator. So now I'm going to subtract 100 from both sides, and I should have probably put the 1 over molarity in there, but I did not. So then you're going to subtract, and there I stuck the molarity back in. And when you are all done, k equals 0.0600, molarity to the -1, seconds to -1. And what I want you to notice is that those units are still consistent with second order rate. Remember, we're back in section even like 13 point, I think it was 2, that those units are consistent with second order. If you recall, what's the first order's units? Just seconds to the -1st. A second order reaction has the units of molarity to the -1st, so seconds for the -1st. So again, our units are very consistent with a second order reaction. So next, the question is, what is the half-life for this reaction? Go back and figure out what is the half-life equation. There it is. Again, I don't believe you're going to have to memorize this because it's not on your equation sheet. If you're ever going to have to know this, it'll be given to you. And so now I'm going to put in the values. And what do you notice about molarity? Molarity is going to cancel out. So what does that leave us with? 1 over 1 over seconds. And so if you're going to rationalize this denominator, that you're going to see that seconds are going to end up on top. So when you are all done, you do get 1666 seconds. Okay, or probably with sig figs, it should be probably 1670 seconds. So there you go. Hopefully you were successful in solving that problem. So let's now look at problem number 17. Okay, it says that a decomposition reaction with a rate that is observed to slow down. As the reaction proceeds, it is found to have a half-life that depends on the initial concentration of the reactant. Those two things are very important to answer the question. So before we answer A, B, or C, the first thing that you need to consider is this going to be a zero, first, or second order reaction? Why don't you pause this and think that through yourself, and then we'll come back. Okay, so how did you do? Well, let's talk about a zero order first. Here is zero, and here is our equation for a zero order. Notice it does depend on the initial concentration. But the question then is, does it slow down? What I would like you to do is go back to page 5 in your notes. And what do you notice about zero order? Okay, here's rate. That's what we're talking about. That's, as I said, they said the rate will slow down. Is the rate slowing down here? The answer is no, it is not slowing down. So no matter what the concentration of your reactant is, okay, it is not slowing down, it's remaining constant. So if the concentration of the reactant in a sense is going down, the rate is constant. So it does not fulfill that requirement. So let's go back to page 16. Okay, so let's talk about first order. Well, the first order's half-life is this, and this doesn't make a whole lot of sense because it is not dependent on the initial concentration. Nowhere is there A naught. So it's not first order. So what about second order? Well, here is my half-life. Oh, I do see the A naught, so it does depend on the initial value. And let's go back to page 5 real quick again. So here we look at the second order rate. What happens as A goes down? What happens to the rate? Rate also decreases. You can say the same thing with first order. As A goes down, so does the rate. But we already eliminated that because it's not dependent on your initial amount. So only the second order is dependent on the initial amount from the half-life equation, and the rate will decrease as the concentration decreases as well. So this is a second order reaction. Let's go back to page 16 and see which A, B, or C answer now makes sense. All right, so knowing this is second order, a plot of the natural log of concentration of the reactant as a function of time is linear. What do you think about that? I hope you all said no, that's a first order answer. So if the answer was first order, then A would make a lot of sense. So A is wrong. How about letter B? The half-life of the reaction increases as the initial concentration increases. What do you think about that? Well, let's take a look at this equation here. So if this amount increases, does this increase as well? Well, if it's in the denominator and the denominator gets bigger, what's going to happen to this number? This number is actually going to get smaller. So that B is wrong. So hopefully C is right. Let's see if that makes sense. A doubling of the initial concentration, the reaction results in a quadrupling of the rate. And that is correct for a second order. If you go back and look at page 5 again, I won't do that for you, but that is true. That is really a definition of what a second order reaction is all about. Okay, let's see what's next. All right, so this is about the integrated rate laws for reactions with more than one reactant, kind of like what we did in section 13.3. We first looked at the decomposition reaction, and then we looked at the rest of it. So how do we go about dealing with this? Well, you have to contrive the experiment so that one of your reactants has a much greater concentration than the other one. Or if you have 3 reactants, that 2 of them will have a much greater molarity concentration than the third. So examine the rate with one reactant and very low. I don't know why I have question marks here. Concentration, the others are much higher. So in this case, we're looking at 3 reactants at certain orders of A, B, and C. So now we're saying if B is much, much greater than A and C is much, much greater than A, so that A is the one with a very low molarity, then B and C do not change as greatly relative to the concentration of A. So you have like a pseudo first order, or perhaps second or zero order, whatever this up here is, okay? So then really the entire reaction depends on A. So it says simplification yields a rate order of a particular one. So problem 18 really kind of brings this to light. Let's check out problem 18. It says consider this hypothetical reaction where you have the rate law, here's your rate, is equal to K times a to the first, notice we left out the exponent, b to the second, and where did c go? Well, if c is left out, it's zero order, because what's c to raise the zero order is 1, so we can just eliminate the c value there. So it's to the first order of a and second order of b. Now look at the experiment. Notice that A is basically 0.01 or 1/100th of a molarity. B is 3 molar and C is 2 molar. So A is the very, very small molarity compared to the other two. So how do we figure this out? Well, because A is the least concentration, the rate really depends on just A. So we look over here and we say it's first order A, so the pseudo order is going to be first order A. So now it says calculate K for the reaction. They give you time, they give you initial molarity, and they give you, after a certain amount of time, that concentration. So what equation are you going to use? Think about it. Well, I sure hope you came up with this equation right here. This is my first order equation with time and the two different concentrations. So let's plug in some values here. Here we have the natural log of the concentration of A at 8 seconds. And here is this. And then I plugged in the values. And so the natural log of this is -5. Natural log over here works too. And I left out a couple steps, but hopefully you got the hang of this. I got K is equal to 0.121 1/seconds. Again, remember what I said in the prior one. This unit is consistent with a first order. All right, so let's calculate the half-life. Well, obviously, what do we know about the half-life? Half-life is equal to this equation here. And then it's equal to, plug in some values. Here's a natural log of 2, and here's my K value. Look what happens to the 1/1/s. And there you go. Now, does that make sense? All right, and hopefully the answer is yes, because this is just under, excuse me, just under the, the 8 seconds is just, I'm sorry, a little over this value here. So if I have a half-life of 5.72, then I would have a concentration of half of this, which is 0.005. Well, look at the problem above. We have 8 seconds here, and that's a little bit above 1 half-life, so I should expect this to be a little bit less than 0.005, and I got 0.0038. So this makes a lot of sense to me. So now it says calculate A of the concentration after 13 seconds, okay? So again, why don't you try this first? Pause this and see how you do. So I put out all the work for you. Hopefully you got A is equal to e to the -6.18, which is 0.0021, which again makes a lot of sense because how many half-lives is that? It's a little over 2 half-lives. So I should be a little bit beyond, or a little bit less, I should say, 0.0025, which this number is. So again, this makes a lot of sense. Now, what I really like about is letter D. Calculate the concentration of C after 13 seconds. Oh, wait a minute. We're talking about C? C? That's not A. How are we going to do this? Well, set up your BCA table. Do you remember doing that? So here's your BCA table with your initial amounts. But after 13 seconds, how much stuff do we have? How much A? We have this much. So what did we subtract by to get this number? Well, if you do your math, it's about 0.008, isn't it? So then what? That's how much C is for A. So how do I figure out this number? Well, take this number, multiply by 2, you get 0.0, I think it's 16. So what is 2 minus 0.016 is roughly that, okay? So that would be our amount of C after 13 seconds. Set up your BCA table. Well, if we look at the next page, you can do this yourself. Go to page 615 and fill it out. And this is a good kind of like study tool for you. That's about it. Hopefully this was helpful. We'll be assigning some homework problems a little bit later. Have a good day.